Hello everyone, welcome to GATEFORUM. So let's start this video lecture. So in this YouTube channel, I welcome you all to this session. So in the last video, we have discussed weightage of strength of metal for the GATE examination and idea how to prepare strength of metal subject for mechanical civil if you are appearing in the coming GATE examination. Okay. Now in this video or in this series of video, I will be covering some of the chapters or almost all chapters in very short so that you can come to know the chapter, that how the chapter should be done and how concept should be made like this only, and the concept should be deal here in the best way so you can have very good idea of the subject so that you can prepare yourself also. Okay, so here this is the first lecture. Here we have chapter 1 in the strength of material. So here we have subject strength of material, that too here we have chapter number 1 here. Okay, so in chapter number 1, here we have lecture 1 here. Today is the lecture number 1 here. And this lecture, we will start our topic, first chapter, that is simple stress and strain. Simple stress and strain is our first chapter. So already in the last class, in the last video, I have discussed that this chapter plays a very important role in the GATE examination because 100% guarantee of coming at least 1 to 2 question. That means 2 to 3 marks out of 100 marks. 2 to 3 marks out of 100 marks in the GATE examination. That's why chapter 1 is very important. Simple stress and strain is very important. So let's start. Okay, so we'll come with the introduction of strength of material. Okay, so here if you go for strength of material, okay, introduction of the strength of material. So basically what is strength of material subject? So strength of material subject deals with the strength. And what is strength? That means suppose if we go for particular design, suppose here we have any particular chair, and for this particular chair, suppose here we have particular chair, and in this chair suppose this load is going to be kept here, some load is going to be kept here, let's say 100 kg load is going to be kept here. So how should be the design of this chair so that these pillars, 4 pillars, 1 2 3 4, 4 pillars, 1 2 3 4, 4 pillars of this chair should not break here na? So we should provide sufficient diameter of the leg. Suppose here we have leg having one leg diameter like this, having second leg diameter like this only, third leg having diameter like this only, and here we have fourth leg having diameter like this only. So all the 4 leg dia should be selected in such a way, diameter should be selected in such a way that it should sustain this 100 kg load, and out of 4 legs, any one leg should not break. None of legs should break. Okay, but there should be one thing in my mind only. The dia should not be over and under. Exact dia. What should be the exact shape dia we should use? Suppose if we are using a very large value of dia, unnecessary we are using large value of dia, wastage of money, because we have to purchase the material. Suppose steel chair, iron chair, a plastic chair, whatever the material of chair, definitely we should purchase the material from the market to produce the chair only. So material is not free of cost now. So dia should not be right, D should not be over limit. That means over value is not accepted. Okay, under value is also not accepted. Under value is not accepted. So D should be a particular exact value or approx value. Exact value should be accepted, because if you go for the over value of the dia, definitely loss of money. If you go for the under value of the dia, definitely product will be substandard, it will break, legs will break. Okay, so customer will say that quality of product is not good only. So dia should be exact only. That means every material having particular strength, every material having some internal property to sustain the particular value of stress, that is known as strength of material. So the whole chapter strength, or the whole subject strength of material, deal with this only. That means what should be the maximum value of force it can sustain, what should be the maximum stress it can sustain only. So definitely on the basis of strength point of view. So on the basis of strength point of view, we'll discuss. On the basis of the strength point of view, we should design the things, right? In the real life, suppose if you're going to become engineer in the future, in the real life, construction of bridge, construction of houses, construction of machines, so many things will be constructed, and we should go for. In companies also, construction of mechanical assemblies, components like this only, and nothing should fail. You should design all the things in such a way that no wastage of money should be there and no failure should be there only. That means exact value you should consider. Okay, so this subject is very important. First of all, this is the introduction first of all. Okay, now suppose if you say, sir, that if you say, sir, actually basically here we have one more subject, engineering mechanics, and here we have strength of material. So what is the basic difference? So what is the basic difference? You can say this also, that what is the basic difference now? What is the basic difference? So one basic difference here we have in engineering mechanics subject, we deal with the rigid body. We deal with the rigid body here we have in engineering mechanics. We deal with the rigid body, but what happens in the strength of material, basically we deal with deformable or real bodies. We deal with real bodies here. And what is the difference between real bodies and rigid body? Very simple difference, that rigid body do not exist in the real life. Basically, it's one assumption that a particular body which will never deform. That means the shape and size of body will never change after application of any value of load. That is known as rigid body. Okay. And what about real bodies? All the solids which we can see around us in the whole universe, that are known as real body. It means whenever there will be load will be applied, force will be applied on that material, on that solid, definitely after application of load, it will deform. That means the shape or size can change. And definitely every body will deform. That means the shape and size of every body will change after the application of load, but for a suitable value of load only. Okay, suppose if you're sitting on a steel chair and you're saying that, sir, I'm 100 kg person, I'm sitting on the steel chair for 10 years and the shape and size of this chair is not changing. That means the steel chair is a rigid one? No. For your purpose, for that application, that is your weight is 100 kg, for your purpose, your weight, it is behaving as a rigid one, but it is not a rigid one, because if you offer the same chair to an elephant having, suppose, let's say 500 kg or 1000 kg, then what will happen to the chair? The chair will break. That means load increases and chair will break or chair will deform definitely. So nothing is rigid, everything is real. Okay, rigid is just imaginary concept only. Okay, so in the strength of material, we purely discuss with real bodies, and in the subject engineering mechanics, we purely discuss with rigid bodies only. Okay, so let's start. So in this subject, we will discuss only about real bodies or deformable bodies. Okay, so now we'll go for the stress. But what do we mean by stress? Very beautiful concept. Try to understand, because what happens generally in your college, if somebody will ask you what is stress, so student used to say simply that load upon area. No, this is not it. If somebody is saying that stress is force upon area, somebody is saying force upon area, simply saying force upon area, this is not true. Why this is not true? This is the mathematical formula of stress, force upon area, and not in every cases. Not in every cases means that force applied per unit area, not in every cases too. So this is not correct. So what do we mean by stress? Stress means simply, if I define what do we mean by stress, so simple definition of stress is resisting force per unit area. Resisting force per unit area. Now what is resisting force? A resisting force per unit area. Resisting force per unit area. But what about resisting force? What do you mean by resisting force? So you say, sir, stress is nothing but resisting force per unit area, you have told. Resisting force per unit area, you have told. Resisting force per unit area. Okay, okay. But what is resisting force? Resisting force means intermolecular force. Just look at here. Take one example. Suppose if here we have a rod and there is no load, no force applied on this rod. Let's say the value of force to pull it is 0 right now on this. Let's say the value of force is right now 0. There is no force here. And suppose the distance between two molecules A and B. Two molecules A and B, let's say distance is D here right now. Distance is D here right now here. Now what happened when here no force is applied here, right now force value is 0 here. There is no stretching of the rod here. But suppose if we stretch the rod, if we apply the force, then what will happen? The overall length of the bar increases first of all. If we apply the force, some amount, 100 Newton, 500 Newton, whatever the value of load applied here. Let's say I'm saying 500 Newton. Let's say I'm saying 500 Newton load is applied here. Right now, the overall length increases here. You can see overall length increases. That is the delta L is the change in the length of the rod here, and actual length was L, and actual length was L here. Actual length was basically here. Actual length was L here, and overall length increases by delta L. But what happened to the same molecules A and B here? Same molecule, since the overall rod stretches by some particular amount, so here the distance between every molecule goes on increasing here. So what about A and B? So here, suppose here we have A and here we have B like this only. Here we have A and B. So how much distance increases between A and B? So definitely now distance will be D plus delta D, let's say. D plus delta C. D is the distance between the two same molecules here. That means the distance between the molecules increases. And if the distance between the molecule increases, so definitely what will happen? Definitely what will happen? Just look at here. Here, what I can say, molecule will go away from each other. Now, if we remove this force, what will happen? After removal of this force, suppose if this force is now removed here, now remove this force, now remove force, whatever force applied now remove it. Now what will happen? Again the length will be only L. Again the length will be only L. That means rod will regain. Again the value of force will be 0, let's say. Again the value of force will be 0 here. No force will be applied here. That means we have removed the load. Now remove the force or remove the load. What happened? Again the length is L. Again the length is L here. I can say again the length is L here, and the distance between A and B, and the distance between A and B is again D. Distance between A and B molecules again D. That means what happened? Initially distance between molecule A and B is D, and after stretching distance between molecule A and B increases, and after removal of load again it come back to the original position. That means internally in this condition, internally molecules are trying to come towards each other to regain their original position, and this is known as resisting force R. The internal molecular force. So what is resisting force? Basically, if somebody will say what is R, so R is nothing but resisting force or internal forces or molecular forces or internal molecular forces or restoring forces, or we can call it as restoring forces. Why restoring forces? We can call it as restoring forces because of this force only, that is the force by the molecules, every molecule will try to come back to the original position, and because of these forces the whole body will come back to the original position. So here we have restoring forces, right, or resting forces, internal molecular forces, or restoring forces, or we can say opposing forces, we can say opposing forces, or the most famous name is resisting force. The most famous name is resisting force. So many name here for R, so many name here, that is either you call it an internal force or internal molecular force or resisting force or restoring force or opposing force, like this only. So this is R. And what about stress? Stress is nothing but that resisting force per unit area. That resisting force per unit area is known as stress. Now, some of you might be thinking that why you have said per unit area, why not per unit cross section area? Why not per unit cross section area? I will go for that also. No? That is not correct. Unit area is correct, but cross section area is not correct. I will go for that also. Okay. Now here, so we have defined the stress. That stress is nothing but a resisting force per unit area. Here we have stress. Okay. Now very simple. So since if we go for the equilibrium, when this can be equilibrium, when outside force, that is applied force F, will be equal to the resisting force F. Under equilibrium, these two forces will be equal. Since we can say summation of force in x direction should be equal to 0. So under equilibrium, these forces should be equal. So what is stress? Stress is nothing but resisting force per unit area. So you can write F by A, force per unit. So mathematically you can say force per unit area. Mathematically you can say force per unit area or resisting force per unit area is the meaning of stress, and this is the formula of stress mathematically, force upon area. So I think I have defined the stress. The stress is nothing but a resisting force per unit area, and here in this situation I can say It is equal to the force applied per unit area. Okay, then you might be thinking, sir, why at the starting you said this is wrong? This is wrong. Why you have said, sir? I will tell you why I have said that defining stress in this way, force per unit area is wrong. I will tell just now. Okay, just look at here. So here we have a stress value. So here we have stress value. You can see here. Here we have stress value. So I told you that what is stress? So stress is nothing but a resisting force per unit area, or which is equal to applied force per unit area is stress. And what about unit? If you go for the unit, unit will be either Newton per meter square, or you can say Pascal. Newton per meter square, or you can say Pascal only. Now, why not cross section area? If somebody is saying stress is a resisting force per unit cross section area, then this is wrong. Then this is wrong. Why this is wrong here? Because it might be happen that we are going to find the value of stress on the different plane. If we are going to find the value of stress on this plane, if suppose this is the selected plane, if this is the selected plane on which we can find out the value of sigma and tau, on which we can find out the value of sigma and tau, normal stress and shear stress. So on the selected plane, this is the cross section area. This is A. This is cross section area A. But what about this plane? Here we have area will be like this. Here area will be like this. On here we have area A dash, which is greater than A, and this area is not cross section area. This area is definitely more than cross section area. Na? So not always cross section area. It can be anything. If area will be like this, if we have a rod here and load is applied here, let's say F load is applied here. So you can't write sigma is equal to F by A. You can't write. This is wrong. Because here we should not go for this area A. We should not go for this area. Instead we should go for this area. Which is, let's say, A dash here. So this here we have sigma on this plane, normal stress on this plane, and this sigma will be equal to perpendicular to this plane, and this sigma will be equal to whatever the value of a resisting force on that plane divided by A dash, you can say. But you should not write A only. So not always cross section area. Most of the students used to do this mistake. Always they are writing cross section area, but no. Whatever the plane on which we are finding the value of stress, that area we have to consider, not always cross section area. Please remember it. Write a note point here. Not always cross section area. Okay. Whatever the plane on which we are interested to find the value of stress, or whatever the plane on which in examination you have to calculate the value of stress, that plane or that area we have to consider, but not always the cross section area. Okay, very simple concept here. So we have done stress. Now types of stress. So basically in types of stress we have a normal stress and shear stress basically, and in normal we have in normal stresses we have direct normal, bending stresses normal, then tensile as well as compressive stresses subcategory here we have. Okay, so generally what happen whenever we have, just look at here, whenever we have whenever we have any area and it's perpendicular, just look at here, perpendicular to this area, perpendicular to this 90 degree here. So this will be normal stress and this will be shear stress. So sigma will be normal stress. And what is the meaning of normal stress? If the resisting force, if the value of R, if resisting force is perpendicular to area, that in that situation, the stress will be normal stress. And what about tau? Tau is the shear stress. Shear stress means whenever we have a resisting force R parallel to area, so we can say it is shear stress. But definition wise both will be same only, but in one situation whenever resisting force perpendicular to area, whenever resisting force parallel to area only, the direction difference only na. So here we have suppose say sigma, this is also resisting force per unit area, and here shear stress tau will be also resisting force per unit area here. So formula will be same for both, unit will be also same for both, but the meaning is different. In one situation resisting force should be perpendicular to the particular area on which we are interested to find the value of stress, and in shear stress our resisting force should be parallel to the particular area. Okay, so here we have different two types of stress, normal as well as shear here we have. Okay, simple, we have done this. Okay. Now, special concept on stress. What is the special concept on stress? This is very important because most of the students used to think only resting force permanent area. But no, stress means, suppose if I define stress, a different style to define the stress here. You can think like this, that sir, this is very unique definition you have seen in your life. So very unique definition of stress, a unique style to go through the stresses. Okay, so basically stress means, if suppose if somebody will say me, well, what do you mean by stress in any interview, I will say just disturbance of molecules. I will say disturbance of molecules, disturbance of molecules against will of molecule, against will of molecules, against will of molecules, nothing else only. This is the meaning of stress. You will say, sir, very unique definition. We have not seen even in books. Yeah, definitely. Because what happened? When stress will be generated inside the body, suppose here we have a human being. Suppose if we have a human being, suppose somewhere here, suppose if we have a human being here, what do you think when this human being will be in stressed condition, when stress will be generated inside this human being, if somebody will disturb this human being against the will of the human, suppose let's say very small child of class 1 2, suppose when stress will be generated inside small kids, suppose if you allow, suppose if child is willing to play right now, if child is willing to play right now, if you allow the child to go and play, there will be no stress generated inside the body of the child because you are not disturbing the child. Okay, but what happened, suppose if child is willing to play right now, and if you are holding the child in your house, everybody is playing, every kids are playing, and you are holding your child inside the house, then what will happen? The stress will be generated inside his body. In the same way, what happened in the metal, we have molecules. In the metals, we have so many molecules, and what occurs? So many molecules here in the metal. If we disturb the molecules against the will of the molecule, then there will be stress. Suppose if you pull it, if you stretch it, then what will happen? Two molecules will be separated from each other. Two molecules will be separated from each other, and they will try to come back to the original position. They will try to come back to the original position with the resisting force R. So they are trying to come back to the original position because you have disturbed it. You have applied the force, tensile force on the body to stretch the body. That's why molecules inside get disturbed and they try to come back to the original position. They try to restore themselves. That's why there is stress. So whenever there will be some disturbance to the molecules, molecule will try to resist or oppose the disturbance. Molecules will try to resist or oppose the disturbance, and due to that only stress will be generated inside the body. Stress will be generated inside the body. So here, just look at here. If you apply some force from the outside, so definitely stress will be generated, and stress is nothing but resisting force per unit area. Okay, but what happened? What happened? Length, overall length increases by delta L. Overall length increases by amount delta L. Here we have. Now what happened? Suppose what happened? If here we can say, if suppose there is a rod which is heated here. If there is a rod which is heated here with the help of heat, what happened? The length increases by amount delta L. The length increases by amount delta L. If length increases here, so what happened to the molecules? Definitely molecules will also separated from each other, but the value of stress will be zero here. Then you will say, sir, how? Here molecules separated, sir, and here we have stress. But here molecules separated and here no stress. Yeah, definitely. Because there is one word, disturbance of molecules against the will of the molecule. Here in the case of it, molecules are willing to go away from each other. That's why there is no stress. That's why there is no stress. Just take an example. Suppose in the summer season, you don't want to sit very close to each other. Even though you all are friends only, suppose you're going in a train, you don't want to sit very close to each other on particular seat, but in winter season you will allow your friends to come and sit. Instead of 3 you can able to sit 5 also, but in the summer because of heat you will try to go away from each other. So since suppose you consider yourself as a molecule, so if you're trying to go away from each other by your own will, nobody is disturbing you, nobody is forcing you, then definitely the value of stress will be zero. Because here in case of heat, molecule will means the whole body will expand. Expansion will be there due to the heat only, and molecules are willing to go away from each other because of the heat only. That's why there is no stress here, no resisting force here, no opposing force here, because molecules are willing to go away from each other because of heat only. But in the first situation, you have applied the force from the outside. Molecules are not willing to go away from each other. So what happened? They will try to come back to the original position with the help of resisting force R, and that's why there is a stress R by A, that is a resisting force per unit area. I think understood. This is very special concept, very special definition of stress. So what is stress? Basically disturbance of molecules against the will of the molecule. Very, very, very unique definition, unique style to define the stress. Now you have understood that what is stress basically. Okay. Suppose if somebody is saying that here we have a rod. Suppose somebody is saying here we have a rod and this rod is rotating. Suppose here about the center, this rod is going to rotate. If this rod is rotating, suppose let's say this rod is rotating. So what will the value of stress? There will be stress, yes or no? There will be no force from the outside, even though there will be stress, yes or no? Yes, definitely there will be stress. Definitely yes, stress will be generated inside the body because of the rotation only. Because if a rotation will be there, all the molecules will be shifted to the outer side because of the centrifugal force. All the molecules shifted to the outer side because of the centrifugal force, and after rotation stops, all the molecules will try to come back to the original position. And when molecule try to come back to the original position, that means definitely there will be some resting force. Definitely there will be some stress. Okay. Suppose if you drop some metal pieces, suppose if you drop one metal rod from some height here to the ground here you drop this to the ground. So is there any type of stress inside this? Is there type of stress? Yes. The stress will be developed or generated inside this rod here. Why? Because if you drop it, what happened? During the drop, what happened? It will go and hit to the floor. It's kinetic energy. Initially at the height, here we have potential energy. Now there is some motion, right? Velocity is kinetic energy here. When it's go and strike to the ground only, then what happen? Molecules will be disturbed inside. Molecules will shift to the bottom, and after some time it will restore themselves only. So definitely here we have, due to rotation also here we have stress, due to drop here also we have stress, like this only. So many types of disturbance will be there. Because of that, stress will be there inside the body. Okay, very special concept of stress. Okay, now here we have types of stress. That normal stress. Yes, somebody will say that what are the types of stress. So you can say, okay, types of stress means, suppose here we are saying about stress. So stress means here we have one is the normal stress sigma, another will be the shear stress tau here. And in normal stress here we can have different types of stress. For example, direct axial stress here we have. Direct axial stress, direct axial normal stress, then bending stress is also, normal stress. And this direct axial stress can be of either two types, either tensile or compressive, and bending stress can be also of two types, either tensile or compressive. Here I can say either tensile or compressive. And tau will be either direct shear or torsional shear, either direct shear, or we can say torsional shear, So here we have type of stress. Normal shear, and in normal we have further category. Direct axial bending stress, and both can be of two types, tensile and compressive. Now what is tensile? If we pull it, suppose if we stretch it, suppose here we have a rod, and if we try to pull it or try to stretch it like this only with the force here, so this will be known as tensile. Here, should I write tensile full form tensile here? And suppose here we have a rod and you want to just reduce the length of the rod. This is known as compressive stress. So here we have C, that is compressive. Here we have compressive. So here we have sigma T, tensile, and here we have sigma C, that is compressive stress. Because in tensile length increases, in compressive length decreases. So we have done stress and types of stress and special concept of stress. I think you are enjoying a lot. What happened in GATE examination? Suppose you are going for the next GATE examination. Let's say you are going for GATE 2025. suppose you are going to appear in gate 25, you are going to appear in gate 25 or 26, 25, 26. So what will make you the topper? What will make you the topper? Two things only, nothing. First thing, the concept should be best, not bookish language, not the definition written in the book, not the formula simply written in the book. No, 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 not like that. Gate exam is not a semester exam, first of all. Okay, very good concept. First of all, concept should be best. First of all, concept should be best. First of all, let me tell you about myself. Right, that I'm not telling my name, but I'm telling that I'm teaching for last 10 to 15 years. Okay, and I have trained so many students. First of all, and second thing, I have analyzed the paper of last 32 years in the best possible way. And after my analysis, I come to know that the concept should be prepared in a particular way, in a special way, so that you can able to solve the question in the gate examination within very less time with very high accuracy also. So concept should be very, very, very good. And one thing more, let me tell you about myself, that I have also qualified gate exam so many times, and I have done my MTech and PhD from IIT Kharagpur also. Okay. Okay. So concept, first thing, concept should be best. And second thing, lot of practice should be there for the questions. More practice would be needed. Suppose after your teacher, suppose I am teaching you in the paid course, suppose I have completed the syllabus and I have done 100 questions. Suppose after my completion of my subject, you should go for 200 questions for practice, so that you can make yourself confident, you can make yourself means very fast, accurate, confident like this only, so that you can be the topper of next gate examination. Okay. Okay. So here we have stress, and here we have a special concept of stress, that what is stress basically. And here we discuss types and stress only. So I think you can enjoy here that what is basically stress. What is basically stress here, I think you have come to know here. Okay. Now stress tensor for 3D and 2D. So what is basically stress tensor? Just look at here. Stress tensor. Here we have stress. So here we have two types of stress, normal and shear. Suppose here we have 3D. Suppose I'm taking one cube here like this. One cube here. So what is the meaning of stress tensor basically? What is the meaning of stress tensor basically? And remember one thing, I'm teaching you this chapter here in the best possible way, but this is not a full course. Okay. So going through one chapter in 1 hour or 2 hours is not complete, because in full course, one chapter can be done in 20 hour, 10 hour, 15 hour like this only, not in 1 hour. Okay. Even though I'm trying to discuss the good things here in 1-2 hour in this video, so that you can enjoy a lot. Okay. Now just look at here. Here we have a cube. Suppose here we have a cube, and 3 axes. Here we have suppose x axis. Here suppose we have y axis, and here suppose we have z axis like this only. Now what happens? Suppose if we go for this face only. So this face, if I draw a perpendicular line to this face, so obviously this will be x axis, and the plane will be, this plane will be known as. Suppose I should shade this plane. So definitely this plane should be YZ plane, I can say. This plane will be YZ plane. Here we have. This plane will be YZ plane. Here we have, or it is also known as X face. Why X face? Because perpendicular to the line, perpendicular to this surface will be X axis. That's why it is X face only. So here we have stress in the X direction. And suppose if we go for, two different direction also, stress will be in this direction also on this plane, that is, this is tau xy. Shear stress on X face in the Y direction. Side here we have, this side here we have tau xz, here we have, that is shear stress on the X face in the Z direction. Now similarly here we have, sigma y, and similarly here we have tau yx, that is shear stress on Y face in the X direction. And here we have tau, and here we have tau yz like this only. Same thing here we have sigma z. First of all, here we have sigma z, and here we have this one, that is tau zx, and then here we have tau, then here we have tau zy like this only. So here for 3D, what I can say here for 3D, total 9 elements here we have, total 9, 3 on every faces. So here stress tensor for 3D, will be represented like this, For 3D you can write in this way, that here we have a sigma x, first of all sigma x, then tau, okay, tau xy, then here we have tau xz like this only, then here tau xy, sigma y, and here we have tau yz. Here we have tau yz, sorry, yx, not here. Just a minute, just a minute. Here we have not xy, just a minute. Okay, just look at here. Okay, here we have yx, here we sigma y, and here we have yz, like this only. Because the first row is x phase, first row is for x phase, and the second row is for the y phase. Second row is for the y phase, and third is for the z phase. Third is for the z phase, here we have. And tau, here we have tau zx, then tau zy, and then last here we have sigma z, like this matrix. Here on matrix we can write in this way. Okay, so diagonal will be normal stress and rest will be the shear stresses. Rest will be shear stress and complementary shear stress will be equal. We can say that tau xy will be equal to tau yx, and tau xz. Tau xz will be equal to tau zx, and tau zy is equal to tau yz, is equal to tau yz. On the basis of magnitude, this will be equal. So you can say this tau xy will be equal to tau yx first of all, and the second thing you can say that you can say in this way, that tau xz will be equal to tau zx. Okay, and third one, the different color I am marking here, different color here we have, let's say with green color, here we have tau, yz equal to tau zy, here we have. So black equal to black, red equal to red, and green equal to green, red in the magnitude wise. And here diagonal will be the normal stresses, sigma x, sigma y, sigma z here. And this is the stress tensor for 3D. And what about 2D? If you go for the 2D, now just look at it. If you go for the 2D stress tensor, so 2D stress tensor, we have only this. Only this will be 2D. Only this will be 2D from here to here. This will become 2D. This will become 2D like this only. That was only tau x, y. Sorry. Here we have 2D. Not here. Just a minute. Here we have 2D. Here we have, this one is the 2D. That is, we have sigma x, then tau xy, then we have tau yx, then we have sigma y, like this only. Here we have 2D. So here we have 4 elements, here we have 9 elements. Okay. And stress and strain both are tensor quantity. Why tensor quantity? Because here we have stress tensor, na? 9 elements here we have. So stress and strain both are tensor quantity. Please write a note point. Stress and strain both are tensor. Both are tensor quantities. Tensor quantities. Tensor quantities, not scalar, not vector. Not scalar, not vector. Somebody will say stress is a vector quantity. Stress is a vector quantity. Say no, not vector quantity. Stress tensor. Because here we have three things. In vector we have magnitude and direction. But here we have three things. Magnitude, direction, as well as plane. Here we have. Here we have first of all magnitude. Then second thing is the direction. And third thing is the plane here, on which plane we are going to find the value of stress. So that's why it is a tensor quantity. Here we have 9 elements. Here we have tensor quantity. Magnitude plus direction plus plane, we are finding the value of stress. 9 elements here we have, that's why it is a tensor quantity basically. Okay, very simple. I think you understood. And here these things will be used in chapter number 2. In chapter number 2, this will be used much. That is 2D stress tensor, you can say. Here, this will be used much in chapter number 2. That is sigma x, sigma y, tau xy during the Mohr circle. During the Mohr circle, this will be used much in next chapter, second chapter Mohr circle. What is the value of sigma x? What is the value of sigma y? What is the value of tau xy? Okay, so this will be used. So please remember this stress tensor at least for 2D, because 3D is not in our syllabus. Try to remember for 2D at least. Try to remember for 2D at least. Okay. Okay. Now we'll move to the here stress tensor in 3D. Here we have topic also. So what happens if suppose you go for the vector quantity, na? Suppose you go for the vector quantity. So what is vector quantity? Suppose we go for vector quantity. So in vector quantity we go for the velocity, let's say. Velocity, let's say. So velocity in the x direction, comma velocity in the y direction, and velocity in the z direction. That's it only. Nothing only. So here we have basically three terms only. Three terms only. So here we can have three terms only. Here we can have three terms only. But what about stress and strain? What about stress and strain? So if you say stress and strain, na, so stress and strains are basically tensor quantity. Basically tensor quantity. How many elements here we have? 9 terms here we have basically. Here we have 9 terms here. So 3 means 3 raised to 1, and here we have 9 means 3 raised to 3 square 9 here. That's why stress and strain are known as second order tensor quantity. Known as second order tensor quantity. Second order tensor quantity. Second order tensor quantity here we have. Okay. Very simple. What is stress tensor for 3D and 2D, and what is vector quantity, and what is tensor quantity, and why is stress and strain are second order tensor quantity. Very simple. Very simple. So the concept should be best. Okay. Bye all of you. Bye.